Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about the module Diamagnetism and Paramagnetism of Atom Part 2, and this paper is from Solid State Physics. So students, let us see what we are going to learn in this module. The first important thing is the quantum theory of magnetic susceptibility. So why quantum? Because already I have explained earlier in part 1 that classical theory is insufficient and unable to explain the magnetism. So naturally you have to take the help of the quantum theory. And secondly, you are going to learn about diamagnetism, and third about paramagnetism. So magnetism of atom is divided into two parts. One which is called as the diamagnetism, and the second is the paramagnetism. And of course, as I repeatedly say, there is a tussle between the quantum and the classical in trying to explain magnetism. So for diamagnetism, how does it occur? It occurs due change in orbital momentum by an externally applied magnetic field, or simply we can say by an applied magnetic field. On the other hand, paramagnetism, it occurs due to contribution from spin and orbital angular momentum about the nucleus. So you see the difference, where in the case of paramagnetism you also have a contribution of the spin. So students, think about the difference between the two, and this is basically like what you get to learn from your undergraduate and your school level studies. Paramagnetism originates from permanent magnetic dipole, and at the same time the magnetic susceptibility is positive. On the other hand, diamagnetism does not require any permanent magnetic dipoles, and also the magnetic susceptibility is negative. So you see, para is positive, di is negative susceptibility. Para requires a permanent magnetic dipole moment, while diamagnetism, it does not require no permanent magnetic dipole. So we will start here with the quantum theory of magnetic susceptibility of atom or ion. Now consider a system at temperature equal to 0, having n magnetic ions per unit volume. The T equal to 0 is actually, of course, an ideal case, but theoretically is the simplest thing that you can do, and also very naturally, because before we go on to a finite temperature system, we need to sort of study the T equal to 0 system. So that's why we are considering here a T equal to 0 with n magnetic ions per unit volume. The magnetization is defined as follows: m as a function of Ba is equal to minus n multiplied by the partial derivative of En as a function of Ba, and this partial derivative with respect to Ba. So what are these quantities which are appearing in this formula? It's EnBa is the nth state energy in the presence of applied magnetic field Ba, and MnBa is the magnetization, which depends of course also on the externally applied magnetic field Ba. In the case T not equal to 0, of course, remember the system will be in the excited state EnBa. So here in this case, if you are considering T equal to 0, then it is like better that the small n that is appearing in M and E you can say equal to 0. So you can say that Mn is M0 for the t equal to 0 case, and En is equal to E0 for the t equal to 0 case. The corresponding magnetic susceptibility for the finite temperature T is given by this expression, is equal to mu naught partial derivative of m with respect to Ba, which further can actually be rewritten in terms of the F is the Helmholtz free energy, and the magnetic susceptibility depends upon the Helmholtz free energy F. Of course, in thermal equilibrium at temperature T, the thermal average of the magnetization of each excited state En as a function of Ba is given as the magnetization, as what we have written down here. Now, before proceeding ahead, we have written down here relation between the magnetization and the free energy. So this magnetization is related to free energy F like this: m is equal to minus n partial derivative of F with respect to the applied magnetic field Ba. And here, of course, as we mentioned before, the total number of atoms are ions. Now, what about the free energy? We are sort of repeatedly saying the Helmholtz free energy. So what exactly is this free energy? So the free energy F is equal to exponential of minus F divided by kBt, which is equal to, again, sort of, you can rewrite this expression like this, that is equal to minus En as a function of Ba divided by kBt. So what do we gain by this? At T not equal to 0, at thermal equilibrium, the magnetization can now be rewritten as m as a function of Ba and T is equal to summation over n Mn function of Ba exponentially e raised to power minus En by kBt divided by the exponential minus En divided by kBt. So this is in thermal equilibrium, remember that. Now we need to determine the energy shift induced by a magnetic field in order to calculate the susceptibility. So in this slide, we will basically talk about the Hamiltonian of atom or an ion in an external magnetic field. So this Hamiltonian is written like this. I'm sure that you might be familiar with this kind of Hamiltonian. So this Hamiltonian is equal to 1 by 2m summation over iota multiplied by vector pi minus e by 2 ri cross Ba whole square plus g naught into mu b s dot Ba. So if you have to identify what are these terms, you will see that, and the part of it is the energy in the presence of this magnetic field. So if you if you put Ba equal to 0, there is no external magnetic field, you will get to see that the Hamiltonian is simply pi square by 2m, which is simply the kinetic energy. So you get to see that, like, when you apply a magnetic field, how the simple kinetic energy actually changes. And remember that this Hamiltonian is also a Hermitian. It's very important. You should know what exactly is a Hermitian Hamiltonian. Now here, what we do is that we take the external magnetic field to be in the z direction, and repeating again, the first term of this equation is the kinetic energy, while the second term is the interaction energy due to the electron spin. So spin plays a very important role. It interacts with the external magnetic field. Note that the vector potential A is equal to minus half of r cross Ba. So you see that the first part, the kinetic part, energy part of this Hamiltonian, contains the vector potential also, which basically modifies the original kinetic energy of the atom or ion in the absence of magnetic field. And the vector potential satisfies the equation, very well known equation, which you might have studied in your electromagnetic theory, is Ba is equal to del cross A and del dot A equal to 0. Now what we will study in this slide is the change in the Hamiltonian on applying the external magnetic field. So the Hamiltonian, now when you apply a magnetic field, and in the absence of magnetic field, you get to see a change in Hamiltonian, which is delta H. And what is this delta H, which is now shown in this equation, is equal to mu naught in brackets L plus G naught into S multiplied by BA plus E square divided by 8m B naught square summation over xi square plus yi square. So I'm sure that the last part actually would remind you of the fact that this magnetic field is actually generating some kind of a circular path, as you can see, xi square plus yi square, which basically tells you this. And also here h cross vector L is equal to the summation over I Ri vector cross Pi vector. And this is quite a very familiar result. You might have studied in classical mechanics that what is the angular momentum, which is basically R cross P. This is exactly what it is. Now let the energy En change by delta En on application of the magnetic field. So what we will do is that in the second order perturbation theory, we can write down this change delta En as this, that is the expectation value of delta H with respect to the wave function plus this second order term. I am sure you must be familiar with the first order and second order perturbation theory in quantum mechanics, which you are applying here. Note that this m is not equal to n, and where this phi n is the eigenfunction of the nth energy state. Now substituting delta H from the previous slide we had shown into this equation of delta En, and we retain terms up to quadratic in this magnetic field. This gives us the following expression, lengthy expression, but of course this is one of the most simplest result that one can expect for the change in delta En, because we are sort of truncating the huge number of terms that is being generated simply by using the second order perturbation theory. So we will now apply the above quantum mechanical formalism to understand the origin of diamagnetism and paramagnetism. So we start with the understanding of the diamagnetism. Diamagnetism, ground state energy shift. Solid which are made up of ions where all electron shells are filled exhibit diamagnetism. For such ions, the vector J, when it acts on the eigenfunction, it gives you the L vector and also the S vector, which is equal to 0. All this acting on the eigenfunction gives you a 0. So consequently, from the expression for delta En, we have the ground state energy shift. Simply boils down to this simple expression. It's quite very interesting that if you sort of look at the equation from the previous slides, and then you say you allow the J, S and L vector to act on the eigenfunction, and immediately you will see that this delta E naught, or rather delta En, gives you a very simple expression as shown here. So once you have this in thermal equilibrium, the susceptibilities then is straightforwardly given by this expression. And how do you derive this expression? So you have to basically go back to the previous expression for the susceptibility and take the help of this specific equation, that is Z of average of value of R square is given by this expression as shown on the right hand side of this slide. So you have to make the substitution in the original expression for the susceptibility, and it's quite straightforward that immediately you will get this result. And this expression based on quantum mechanics coincides actually with the one which is derived classically also. So students, in discussing paramagnetism, there are two cases. The two cases are J equal to 0 or J not equal to 0. So let us start from the fact that case 1 where J is not equal to 0, we get contribution from first two terms of the expression for delta En. And in the case 2, when J equal to 0, we get contributions only from the second order term delta En. And also one can derive in detail the magnetization, the expression for which is given as n into gamma j into bj as a function of x, where this b term is very special. It is a function, it is a Brillouin function, and this entire expression for magnetization is called the Curie-Brillouin law, where this parameter gamma is equal to g into mu b. Now remember that how we have derived this is a very important thing to understand, even though I have not shown it in these slides, but just to briefly tell you that we will have to consider the first case. We assume that only the lowest 2j plus 1 states are thermally excited. So therefore, with the applied magnetic field along the z direction, if you remember, the expression for the Helmholtz free energy exponential minus f by kBt is modified, and the summation actually will be like this, that the Jz will go from minus j to j, and then what we have to do is that summing the geometrical progression, we have to like take the help of the summation of the geometrical progression, and using that summing over the geometrical progression, that is exponentially, let's say minus beta into f, you can do this as an exercise where beta of course is 1 by kBt. You can write down the expression for the magnetization as what was shown in the previous slide, where this bj x is the Brillouin function. So bj x is a Brillouin function, which is I have shown here, written down here, is 2j plus 1 by 2j into the Koth function, 2j plus 1 divided by 2j x minus 1 divided by 2j into Koth of 1 by 2j x. Here of course this x value is beta gamma j into ba, which is equal to mu ba divided by kBt. So this is a Brillouin function which like you learn it for the first time here, or maybe some of you might have learned it earlier also, but like this derivation one could actually try it out, not very difficult. Okay, that's why I have not shown it here in the slides. So this figure here actually shows you a plot of magnetization versus temperature. The solid line is the theory while the squares are the experimental points, and you see it's an excellent agreement. So this magnetization divided by mu b versus the b by t, and you see that how beautifully the theory coincides with these experimental values. And in fact this is one of the good motivation to work on this particular field at that particular time when this theory was being developed. Any kind of theory versus experiments, the good matching with theory and experiments actually is one of the major factors of advancement in science. So let us now look at the high temperature case. So in the case of high temperatures, this parameter x is much less than 1. Under these circumstances, the Brillouin function Vj as a function of x is approximately equal to j plus 1 divided by 3j into x, and the susceptibility is basically c divided by t, where c is a Curie constant of T is a temperature. And what is the value of the Curie constant? We will see in a short while. So this Curie constant actually is equal to mu naught n g square multiplied by j into j plus 1 and finally into multiplied by nu b square divided by 3 kb. This is a Curie constant, the famous Curie constant. So students, let us summarize what we have learned in this module on dia and paramagnetism. First, the energy shift induced due to the external magnetic field. We have seen the expression for that. The magnetic susceptibility was calculated from this energy shift. Okay, so ultimately in the magnetic response, the susceptibility is a response function, and this is what we need to calculate, and we did that. But how did we do that? We took the help of the energy shift. The magnetic susceptibility of diamagnetic and paramagnetic substances for different cases was also shown. Thanks for visiting the ePathshala program. Thank you, students.